In this lab, we'll measure the responses of a couple of different filtering circuits. Filter responses include both magnitude and phase, but we're going to only measure the magnitude response. Before we work with some specific circuits, let's do a brief review of filters in general. For filters, the inputs and outputs to the circuit are phasors, but now the phasors are considered to be functions of frequency. The circuit itself is modeled by the frequency response, which is a complex function of frequency. The input phasor is multiplied by the frequency response to get the output phasor. The frequency response, h of j omega, provides the gain and phase difference introduced by the circuit. The gain is the magnitude of h of j omega. It's the ratio of the output amplitude as a function of frequency to the input amplitude as a function of frequency. The phase difference is the phase angle of h of j omega, which is the angle of the output phasor minus the angle of the input phasor. In this lab, we'll only focus on the magnitude response of the filter. The first circuit we'll look at in this lab is a simple RC circuit. We'll measure the magnitude response of both the voltage across the capacitor and the resistor. The thing to notice about this is that the circuit can look like either a low-pass filter or a high-pass filter, depending on which voltage you measure. The capacitor voltage will be high at low frequencies and low at high frequencies, so it's a low-pass filter. The resistor voltage will be low at low frequencies and high at high frequencies, so that's a high-pass filter. The fact that the resistor and the capacitor play opposite roles makes sense. KVL around this loop says that there's a fixed amount of voltage that's shared between the capacitor and the resistor. If the voltage difference is high for the resistor, it has to be low for the capacitor, and vice versa. Before we demonstrate operation of the circuit and make our measurements, I want to point out a way to speed up our data acquisition. Ultimately, there are three parameters we'll want to measure in order to get magnitude responses for the capacitor and resistor voltages. The resistor voltage magnitude response is the resistor phasor over the input voltage phasor. And the capacitor magnitude response is the capacitor voltage phasor divided by the input voltage phasor. To get both magnitude responses, we need to measure three parameters: the capacitor voltage, the resistor voltage, and the input voltage. Sadly, our USB-based oscilloscope has only two channels, so we either have to run separate tests to get the two magnitude responses or come up with a trick to get all three values at once. I'm going to use the tricky approach. I'll use my two scope channels to measure the resistor and capacitor voltages. If I apply KVL around this loop, I'll find that the input voltage is equal to the sum of the capacitor and resistor voltages. So I can create a math channel to add channels 1 and 2 and use that as my input voltage. Then I can acquire all three signals that I need at each frequency with a single set of measurements. This is our RC circuit. Channel 1 of the waveform generator, this yellow wire, is used to apply the input voltage. Ground is at this terminal down here. I'm using channel 1 of the scope, the orange wire and the orange wire with the white stripe, to measure the resistor voltage, and channel 2, the blue wire and the blue wire with a white stripe, to measure the capacitor voltage. Now let's apply power to the circuit and see how it works. First, I'll set up the waveform generator. I'm using an amplitude of 2 volts and a frequency of 200 hertz, which is reasonably close to my cutoff frequency. I'll click Run to apply power and go to the scope. On the scope, I've set the channel 1 and the channel 2 ranges to 1 volt per division and the time base to 1 millisecond per division. If I click on Run, both of my signals at this frequency have about the same amplitude. We'd expect that at the cutoff frequency. But I need the input amplitude to get the magnitude response. I'm going to use a math channel, add channel. It's a simple math channel which defaults to the sum of channel 1 and channel 2. This corresponds to our input voltage, which has a 2 volt amplitude. Now we'll set up measurements to view the amplitude of all three signals. View, measurements. I'll add 3 measurements. They're all predefined. I'll get the channel 1 maximum, the channel 2 maximum, and the math channel maximum. Now I can use the ratio of C1 to M1 to get my magnitude of channel 1, and C2 to M2 to get the magnitude response across the capacitor. Now let's change to a low frequency. Going back to the waveform generator, I'll pick a frequency of 20 Hertz, which is well below the cutoff frequency. Go back to the scope. I need to change my time base. I'll use 10 milliseconds per division. Now I've got my amplitudes of all 3 channels for that input frequency. And finally, I'll look at a high frequency, say 2 kilohertz. Back to the scope. I need to change my time base. It's 100 microseconds per division. Those are my 3 signals. As we'd expect, the capacitor voltage, the blue line, is small at high frequencies because the capacitor voltage looks like a low-pass filter. The resistor voltage is large at high frequencies because it looks like a high-pass filter. Finally, we'll measure the magnitude response of this active filter. This is a high-pass filter, but let's take a quick look at the circuit behavior at low and high frequencies to verify this. At low frequencies, the capacitor looks like an open circuit, so the voltage at the inverting input terminal of the op-amp is 0. That means that the output voltage will be 0 at low frequencies. At high frequencies, the capacitor short circuits, and this circuit just looks like an inverting voltage amplifier with a gain of R2 over R1. This circuit then is a high-pass filter. Now let's demonstrate operation of the circuit. Here's our active high-pass filter. I've got an OP27 operational amplifier here. I'm applying positive 5 volts at the positive voltage input and negative 5 volts at the negative voltage supply. I'm applying the input with channel 1 of the waveform generator. I'm measuring the input with channel 1 of the oscilloscope. I'm measuring the output with channel 2 of the oscilloscope. Now let's apply power and see how this circuit works. First, I need to turn on power to the external power supplies. As I said before, I'm applying 5 volts and negative 5 volts. I'll start out with a 500 Hertz frequency with a 1 volt amplitude at my input. That corresponds to a relatively low frequency for this circuit. Now if I go measure the response, the input voltage is channel 1, the output is channel 2. I've got my maximum values displayed over here. The input amplitude is about 1 volt and the output amplitude is about 0.27 volts. That means the gain of this circuit at low frequencies is about 0.27. We'd expect a low gain at low frequencies since this is a high-pass filter. Now let's change the frequency to something near the cutoff frequency, say 3000 Hertz. The input voltage amplitude doesn't change. It's still about 1 volt. The output amplitude is about 1.3 for this frequency. This is close to the gain of about 1.4 that we'd expect at this frequency. The differences could be due to the fact that I'm not applying a voltage that's exactly at the cutoff frequency, or that the actual capacitance is likely different from the nominal value. Now let's take a look at a high frequency. I'll try 20 kilohertz. Change my time base to, say, 10 microseconds per division. The input voltage amplitude is still 1 volt, and the output voltage amplitude is about 2 volts, which agrees with the gain of 2 we would expect at high frequencies for this circuit. This lab covered both active and passive filters. Keep in mind when designing filters that active circuits require an external power supply, but they do isolate the load from the input.